Welcome to lesson 2, and we previously talked about Lewis structures, and we talked about condensed structures and line drawing, and we worked POGIL exercise 1, in which you do the additional problems. So just a review, so if you have something like this, right here, this would be a just a kind of a condensed, not even, yeah, that would be a condensed formula. And the connectivity is the carbons in the middle, and these two oxygens here would be connected to that carbon, and then hydrogen would be on the other end. So now the total number of valence electrons would be hydrogen is group 1, so it has 1 valence electron. There's 2 of them, so that's 2 from hydrogen. Carbon is group 4, and there's only 1 of them, so that's 4 valence electrons. Oxygen is group 6, and there's 2 of them, so that's 12, and you add this all up, that's 18 valence electrons, and then you do your common bonding pattern. And remember that carbon likes to be in the middle connected, and so you see here that the common bonding pattern, hydrogen does 1 bond and 0 lone pair. Okay, carbon, what's carbon like? Carbon likes 4 bonds and 0 lone pairs. So these are the atoms that have no charge. So we can call them our happy atoms. So carbon needs 4 bonds. Okay, so we'll put a double bond there. And what does oxygen like? Oxygen likes 2 bonds and 2 lone pair. Now you just kind of memorize. So you put your lone pair. So oxygen now has 2 lone pair and 2 bonds. Oxygen over here has 2 bonds and 2 lone pairs. Okay, let's see if we have 18 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 valence electrons. That's correct. And if you check, every one of these atoms have a complete octet. So that is a good Lewis structure. Now I'm going to go ahead and tell you that I think it would be good for you to go ahead and learn your functional groups. I think we don't really do that until maybe chapter 3, but you need to be able to look at these Lewis structures that you're drawing and be able to classify them in a certain functional group. What a functional group is it's a group of atoms that are connected in a particular way, and they function very similarly. So we're going to learn, and if you look in your chapters, they're based on these different functional groups, the chapters are. And these group of atoms will have similar physical properties, which are boiling points and melting points, solubility, and also they'll have similar chemical reactions. And that's how we learn and characterize organic compounds. This particular functional group, this actually molecule is called formic acid. It is a carboxylic acid, and it is what causes the stinging when an ant bites you. So the best way to learn your functional groups would be to divide them in a category with no carbonyl and with a carbonyl. Okay, and a carbonyl is a carbon double bonded with oxygen, and the oxygen has a lone pair, 2 lone pairs, because oxygen likes 2 bonds. Now, what's connected on that side or that side of the carbon can be different. So this is no carbonyl. So if there's also no heteroatoms, so there's no oxygen, there's no sulfur, there's no nitrogen, and no halogen, which is fluorine, chlorine, bromine, or iodine. Okay, so heteroatoms are atoms other than carbon and hydrogen. So if it has no heteroatoms, they are called hydrocarbons because there's carbons and a hydrogen only. So something like this. What is this? This is CH3, CH2, CH2, CH3, and this is an alkane. You have something like this. This is CH3, CH, CH, CH3, and this has a carbon-carbon double bond here. And that is not an alkane, but an alkene, E-N-E. And these are the 4 hydrocarbons. There's 1, 2. You can also have something like this. This is CH3, carbon, carbon, CH3. This is an alkyne, Y-N-E, so that's a carbon-carbon triple bond. Or you could have something that is a ring structure that has alternating carbon-carbon double bonds, and this is called an aromatic. So that includes 4 types of hydrocarbons. So hydrocarbons are one type that have no carbonyl. We'll keep this over here. Okay, we're still doing no carbonyl. And so what if we have heteroatoms? And the heteroatoms we're going to look at just to get started will be just the oxygen and nitrogen and halogens. Okay, so but still no carbonyl, no carbonyl. So if you have something like this, and you see you have carbons, we'll do the CH3, CH2, CH2, OH. This is called an alcohol. Okay, that's an alcohol. And you can see it has the carbon OH. Then you could have something like oxygen. Oxygen likes 2 bonds and 2 lone pairs, so you put your 2 bonds. This is an ether. Okay, so this is an ether. You can see the carbon over here and the carbon over here. If you wrote that out, it'd be CH3, CH2, CH2. Here's your oxygen. And then CH2, CH3. So that's an ether. So that's 1, 2. And then you could have a nitrogen. So if you have something just like this, NH2, and this would have a lone pair on the nitrogen. So what is nitrogen's bonding pattern? Nitrogen likes 3 bonds plus 1 lone pair. If you do the condensed formula, CH3, CH2, CH2, NH2, this is called an amine. And then the other ones you could have is like a halogen. And if you wrote this one out, it'd be CH3, CH2, CHBr, and then CH3. And these are called alkyl halides. And there's 4 of them there. These are all compounds that have no carbonyl group. So no carbonyl group. Now, what about the ones that have a carbonyl? Okay, so now this is with a carbonyl. And let's do no heteroatom. Okay, so no oxygen nor nitrogen. So you could have something like this. This is called acetone. Smells like fingernail polish. This would be CH3. And then you would have CO and then CH3. Okay, and you see how the oxygen has 2 bonds and 2 lone pairs. This is called a ketone, O-N-E, a ketone. Now, if the carbonyl, so this is the carbonyl, okay? If the carbonyl is at the end carbon, so if you have something like this, where there's a hydrogen here, so this is a carbon, CH3, and you got this carbon, and then this CH3. But if you have something like CH3, COH, so this CH3, or that carbon, this is the CH3, and you have this hydrogen here connected to that carbon, this is called an aldehyde. And those are compounds that have a carbonyl but no heteroatom. So that's two groups right there. Now, if you do have a heteroatom, we saw something like this, and this is CH3, COOH. So this carbon is this carbon. This CH3 is here. You have lone pairs on this oxygen, lone pairs on this oxygen. This, with the two carbons, is called acetic acid, and it is the main ingredient, the active ingredient that is in vinegar. So this is in vinegar, and this is called a carboxylic acid. Now, if you have a carbonyl and you have a nitrogen, so something like this, nitrogen has 3 bonds, 1 lone pair, oxygen, 2 bonds, 2 lone pairs. So this is your CO, and then this is your nitrogen, NH2. This is called an amide. So those are examples. The other one we did not put on here is an ester, and an ester is something like this. It would look like this. So there's CH3 here. This is your carbonyl, and then this CH3 is over here, and this is called an ester. And those are very volatile, good smelling compounds that are in the perfume industry. Now, the reason why I think it's important for you to look and start making index cards and learning your functional groups, some students actually get a functional group app. The sooner you learn these, the sooner you're going to be able to write really good Lewis structures and draw them quickly and skeletal drawings. So that should help you. Now, for today's lesson, so start learning those functional groups. But today's lesson is really focusing on kind of a little bit more review of the Lewis structures, but we need to cover formal charge, how to do formal charge. So I'll put my learning objectives here. So you need to be able to do formal charges, assign formal charges to molecules. You need to be able to look at the electronegativity differences. Be able to assign a dipole moment. So we can talk about what those are. And then we're going to finish up with drawing resonance structures. And we'll talk about hybridization and geometry. You also might want to get some molecular models, and we'll maybe do put some models together. Okay, so what we've been focusing on is drawing these molecules, their Lewis structures, where they have no formal charge. Those are our bonding patterns that we've been looking at. But let's say we look at problems that do have charge. So let's say the Lewis structure for NH3BH3. Okay, so here we have nitrogen connected to boron. The hydrogens here are all terminal. And so these 3 hydrogens go on nitrogen and these 3 hydrogens go on boron. So when you do this, this is the structure you get. Okay. Now, we know that nitrogen likes 3 bonds and 1 lone pair. And we see that it has 4 bonds. So because it's not in this bonding pattern, we're going to have to assign a formal charge to nitrogen. Okay, we're going to have to do that. And then what about boron? Boron likes 3 bonds, 0 lone pairs. So we're also going to have to assign a formal charge to boron. So how do you do formal charge? So the formal charge formula, which is on, let's say page 48 of your book, is basically you take the group number, GN, group number that element's on, and then you minus dots and you minus dashes. Okay, so dots are the lone pair and dashes are the covalent bonds. So let's do the formal charge for nitrogen. So formal charge for nitrogen would be its group number, so it's group 5 minus how many dots? It has 0 dots. And how many dashes? How many bonds? It has 4. So 5 minus 4 is a plus 1. So nitrogen gets a plus. Formal charge for boron. Boron is in group number 3. It has 0 lone pairs and it has 4 covalent bonds. Formal charge equals a -1. And you can just put it up like that. If you do plus, you can do plus, or you do +1 and -1. And that is how you assign formal charge. So the key is recognizing when you need to assign a formal charge and then being able to do that. Okay, we'll try another. Draw the structure here. H2CnH2 plus. Okay, so this carbon is got 2 hydrogens connected to it. See the H2, and then it's connected to the nitrogen, and the nitrogen has 2 hydrogens, and you notice this has an overall, the molecule has an overall charge of plus. So what you can do is you can add up your total valence electrons for this. So hydrogen has 1 because it's group 1, and there's 1, 2, 3, 4. So 4 times 1 is 4 valence electrons from hydrogen. Carbon is in group 4, and there's only 1, so that's 4 valence electrons. Nitrogen is in group 5, and there's only 1, so that's 5. And so that's 9, 10, 11, 12, 13 valence electrons. And then the +1 means that you only have 12 valence electrons to work with. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you can do 11, 12, like that. Okay, so now let's look. Is hydrogen happy? Yes, it likes 1 bond, one bond, 0 lone pairs. Carbon likes 4 bonds and 0 lone pairs. Nitrogen likes 3 bonds, 1 lone pair. So this tells you here that nitrogen needs a formal charge. So you do your formula here. Formal charge of nitrogen is group number. Nitrogen is 5 minus how many lone pairs? 0. How many bonds? 4. So 5 minus 4 is a +1. And so the plus sign, this plus here on this molecule, is actually assigned to the nitrogen. And that's how you assign formal charge. if you don't have your formal charge assigned appropriately, you will lose points, and it will be because you do not have a correct Lewis structure if you do not have the formal charge drawn correctly. All right, so the next thing we need to look at is electronegativity. So we talked about how you have ionic compounds like sodium chloride, and sodium is a full positive, and chloride gets that electron as a full negative, and that's an ionic compound. And in water, that would separate into its ions. Well, organic molecules, they have this kind of a push and pull. And so based on the electronegativity difference, will determine the bond polarity. So this will be very important. When you look at electronegativity charts, we have a figure 1.8 in your book on page 47, and this is the Linus Pauling received a Nobel Prize for assigning these charges, or these assigned polarities. Hydrogen has a 2.2, lithium a 1, sodium a 0.9, potassium 0.8. You do not need to memorize these. I'm just put them here for our discussion today. 1.3. These are the elements that you typically will see in organic chemistry, and that is why the whole periodic table is not here. Okay. So oxygen is 3.4, sulfur 2.6, fluorine is the highest with a 4.0. What we all try to achieve is a 4.0. Now, sodium chloride, you have a 0.9, and the chloride is a 3.2. So 3.2 minus 0.9 is a 2.3 electronegativity difference. And so that is a very polar bond, and that would be an ionic compound. And you can recognize this when you have a metal with a non-metal. You're going to have a big polarity difference because electronegativity increases going up a period, okay, up a group. So it increases going up a group, 0.8, 0.91, 2.2, and over. So as you can see, 4.0 is greater than 2.2. So as you go to the right, your electronegativity is going to increase. So if you have a compound like this, okay, it is considered that carbon hydrogens here, if you wanted to draw all your hydrogens in, this carbon has 2 bonds, so it must have 2 hydrogens. The carbon-hydrogen bonds are considered not to have electronegativity difference. So you see a 2.2 and a 2.5. This is considered essentially no difference. Okay, so and that's considered in organic chemistry as non-polar. But now you have chlorine here, and between the carbon and the chlorine, you have a 3.2 minus 2.5, you have a 0.7 difference. And so this is going to be a partial positive where the carbon is, and it'll be a partial negative with the chlorine. And you can also do it like this, where the positive is with the carbon and the negatives with the chlorine. And this arrow means 1 electron, 2 electrons. So the electrons are pushing towards that chlorine, so you have this electronegative cloud here that's going towards the chlorine, and it literally pulls those electrons through. Now, why that's important is we're going to find that when we do chemical reactions here, you're going to have a nucleophile, like let's say you're going to see something like a full charge of oxygen, and that oxygen is going to be so attracted to that positive carbon, and then you're going to see that those electrons will push and go with chlorine. And that's how chemical bonds get formed and we have chemical reactions. So we need to be able to assign a dipole moment within these molecules. So maybe we try a few of these, and you do have extra problems. I've given you problems and worked problems in your book. So that would be good. Okay. So let's just look at maybe well, okay. How about something like this? CH3, CH2, CO, CH3. Okay, so if you draw that compound, the first carbon is here, and then the second carbon is here, and then the third carbon is here, and it's bonded to an oxygen, lone pair, and then we have our last carbon here. So this is a ketone, okay, and of course we could do it like this. Okay, this is our line drawing, and you can see that the carbonyl, this is a carbonyl, and the carbonyl has a dipole. So this is very delta positive, this carbon, and it's being pulled with 2 bonds towards the oxygen. So if you looked at oxygen, you get carbon, nitrogen, oxygen. So electronegativity increases. So oxygen has a higher electronegativity than carbon, and so this would be the negative, and it would pull that electron cloud, and you could see that your electron cloud would be towards the oxygen, so you could do a partial positive there and a partial negative, or you could write the dipole moment this way. Now, if it has a dipole moment, this is this mu, and you would say greater than 0. Now, a compound like this, which is just butane, CH3, CH2, CH2, CH3, basically doesn't have much, it doesn't have much of a dipole, okay? So there's no heteroatom. If you have a heteroatom in your molecule, oxygen, nitrogen, or a halogen, then you need to be looking to assign that dipole, and that dipole, the delta negative, will always be towards the oxygen, nitrogen, or the halogen. Okay, so one of our learning goals was to do resonance structures and hybridization. So let's look at some Lewis structures. Always begin with the Lewis structure. Let's do acetic acid. So CH3CO2H. Okay, so what does this look like? You can draw the Lewis structure. It's a carboxylic acid. And now I want to talk about hybridization, what you need to know about that. Hybridization and shape and geometry. Now, that was a big topic in Gen Chem. Hybridization explains actually methane. So methane, if you make a model, you can draw a model of methane, molecular model with carbon being black and has the 4 hydrogens. You would think that these would be 90-degree angles, these dihedral angles. You would think they'd be 90 degrees, but in reality they are not. Okay, these are actually, each one of these is 109.5 degrees. So what's happening is you have these hydrogens in the same plane, but you have one hydrogen that's coming at you. So the dash, the wedge, you have the wedge is at you. So it's pointing at you. And then you have this dash, and it's going away from you. Okay, and if you draw it with a line here, then this is in the plane. So this is in the plane. So this is like a plane, a piece of paper. And when you do the dashes here, this hydrogen is going behind the piece of paper, and then the one on the wedge is coming at you on the piece of paper. And each one of these bond angles is 109.5 degrees. Now the hybridization of this, hydrogen does not hybridize. To make this covalent bond, it has its valence electron in the 1s orbital. So it has this it's nice little valence electron that's overlapping in this bond, and it's located in the 1s orbital. Now carbon has it has a 2s orbital. They can have 2 electrons, and then it has a 2px, a 2py, and a 2pz. And remember, these are like dumbbell shapes on the x, y, and z axis, and the s is a sphere. Now when these hybridize, they get a new shape. Okay, it's not a sphere, it's not a dumbbell. It is a wiffle ball bat. Okay, so some of the S comes and some of the P comes. Okay, and so now it looks more like this, a wiffle ball bat. I think we can do better. Okay, so P has equal up and down, but a wiffle ball bat looks like that. And so if you hybridize each one of these, if you put in 1, 2, 3, 4 orbitals in, you got to get 4 orbitals out. So if you put them in, you got to get 4 orbitals out. So that means you can get 4 of these wiffle ball shapes, okay? And so that's what happens with methane. So each one of these has carbon has one of its electrons in there, okay? So one of these goes here. That shape overlaps with the hydrogen with its 1 electron. And then the other one here goes like that with its 1 electron. This one goes here with its 1 electron, and this one goes here with this 1 electron. And so this uses 1s, and then it uses 1, 2, 3p, so sp3. So, and you can say, okay, when you look at the Lewis structure of methane, I always say how many things, not bonds, is connected to the carbon when I'm doing hybridization. And I would say, okay, there's 1 thing there, 2, 3, 4, and then I add my sp, and I go 1 plus 3, 1 plus 3 is 4. So this is sp3. And so that carbon there is an sp3. And I have memorized that this is 109.5 degrees bond angles, and this is tetrahedral. Because we got to understand the shapes. Okay, if you understand the shape, you understand the function. Are you going to lay down on a bed? What would you rather do? Would you rather lay down in a chair or lay down in a bed? Lay down on the bed, right? Because the shape is more perfect. If you want to sit down, you choose the shape of a chair. So these molecules all have shape. Now, what if you had, so let's look at, so this carbon here, how many things is bonded to it? 1, 2, 3, 4. So this carbon here is sp3. Okay, and so we know that this carbon here is tetrahedral in shape. Each one of these dihedral angles are 109.5 degrees. What about, and hydrogen doesn't do the hybridization, okay, so it just uses 1s. What about this carbon? Well, how many things are bonded to it? 1, 2, 3. So 3 things. So sp2. 2 plus 1 is 3. So this carbon is sp2. So let's look at sp2. sp2 means you took an s orbital, and you took 2 of these p orbitals. Okay? So you took 1, 2, 3 orbitals to make an sp2. Okay, so to make the sp2, you took 3 of the orbitals, and what do you have left? You have this unhybridized p orbital. So this uses 1 wiffle ball bat to bond to this carbon. It uses 1 wiffle ball bat shape orbital to bond to that oxygen. And it uses another wiffle ball bat to bond to this oxygen. And what's left is this unhybridized p orbital, and that's the pi bond. Do you see that? The pi bond is an unhybridized p orbital. And so that's where the pi bond electrons are. This happens to be planar, so it's flat as a piece of paper. Okay, so there's no dashes and no wedges. Not on something that's planar, it's flat. There's nothing coming at you, there's nothing going back. And each one of these bond angles are, the dihedral are 120 degrees. Okay, so this carbon here is sp2. This oxygen, so what elements do you have to worry about hybridization? Carbon, oxygen, nitrogen. Those are basically it. Okay, carbon, oxygen, nitrogen. So this oxygen, it has how many things? It has 1, 2, 3, 4. You would want to say it's sp3, but it has resonance. Okay, and we're going to talk about resonance, and you'll see because it has resonance, it's going to be an sp2. And that's the topic we'll talk about next time is resonance. We'll draw some resonance structures. Before we leave this, let's look at an sp. So when we look at our, let's look at our hydrocarbons to wrap this up regarding hybridization and geometry. Okay, so hydrocarbons are just hydrogens plus carbons, and we've talked about, let's do this alkane, and you're going to learn that this is called butane. We'll learn that. So this is CH3, CH2, CH2, CH3. We can draw the Lewis structure. Okay, so there's our Lewis structure. We also see that this is alkene. This is actually called 2-butene, ENE for alkene. You'll learn how to name these. We have a double bond here. So we have a multiple bond. And then we'll talk about this compound here, 1, 2, 3, 4, 5. We'll call this pentine, YNE, and that's a 2-pentine. That looks like this. Okay, so and this is an alkyne. So these, every one of these carbons in the alkane are bonded to 1, 2, 3, 4 things. So each one of those are sp3. They're tetrahedral, and they have 109.5 degree bond angles, and you could draw them with 1 hydrogen coming at you and 1 hydrogen going away. These other ones, they would actually be a zigzag because the zigzag shows in the plane of the paper. Now, when you go to the alkene, you have this carbon, and this carbon's bonded to 1, 2, 3 things. So this one is sp2, because if you do 2 plus 1 is 3. Okay, 3 things. And sp2, so this carbon here and this carbon here are both sp2 hybridization, and that means they used one s orbital, they used 2 p orbitals, and they mixed these together to get, they mixed in 3 orbitals to get 3 of these wiffle ball bats shape, and they have 33% S character, and they have 66% P character. The shape of an sp3 orbital would have 25% S and 75% P. Okay, so what's left over is one unhybridized P orbital. You have to have an unhybridized P orbital if you're going to make a pi bond. Okay, it's a requirement. You see how you have a pi bond right there? So that those pi electrons, those 2 electrons, are in an unhybridized p orbital that are above and below the plane. And this is planar. So every bond angle is 120 degrees. This is planar. And those pi electrons are above and below. Okay, what about an alkyne? We see here that we have this carbon here has 1, 2, 3, 4 things. So this is an sp3 hybridization, and that's tetrahedral in shape. So that means there's the dash and the wedge. This carbon here is bonded to 1, 2 things. So that one would be sp. Because if you add the superscripts, you have 1 plus 1 is 2. So 2 things. So it's sp. sp is linear. And the dihedral angle is 180 degrees. So this is 180 degrees. And it's linear. And so what does that require? That requires 1 S and 1 P to make an SP. So when you combine these, you get an SP, which is 50% S character and 50% P character. And so if you have 2 orbitals, because you took 1 S and 1 P, then you better have 2 of these. And these 2 are used to bond the 2 carbons on both sides. What is left over then are 2 unhybridized p orbitals. And that's what you have to have for an alkyne, because you have 2 pi bonds. So you have 1 and one of those unhybridized p orbitals that are above and below the plane. And then you have another one, and this is going to come horizontal. So you got above and below the plane for those pi electrons. And then you go to the next carbon here. So that's an sp and sp. This is going to be an sp3, and this is an sp3. So you need to be able to assign hybridization and shape to these carbon, nitrogen, and oxygen elements. And we'll also talk about resonance the next lecture, and we'll do the POGL activity 2 for resonance structures, and we'll assign major and minor contributors to resonance structures.